This is Ms. Peters, and today I'm going to go over the first three types of intermolecular forces: London dispersion forces, hydrogen bonding, and dipole-dipole forces. Now, I'll talk about intermolecular forces in a second, but these are attractions between molecules, and so they're the reason solids are solids, liquids are liquids, and gases are gases. Now, as you learned, according to the kinetic molecular theory, there are no attractive forces between ideal gases. But as the Khan Academy video showed you, there are attractive forces between real gases, and these attractive forces are what's known as intermolecular forces. So gas particles do interact with each other, just like solid particles do and liquid particles do. So before we get started on that, just going over solid, liquid, and gas. This table, if you need to pause the video right here, you should know this. I'm not going to spend time going over that, but we're going to talk about phases really fast. So a phase is a homogeneous part of a system. So remember, homogeneous, it is not mixed with anything that's in contact with other parts of a system, but is separated from them by a well-defined boundary. And so a perfect example of phases is looking at this picture of glaciers and waters. There are two phases, a solid phase and a liquid phase. Water is ice, where yes, it touches other things, but it is ice. It is separated. It is all one solid. And those molecules are all together. Or it's liquid. And in the liquid, all the water molecules are together. And so solids and liquids are also known as phases. And that will come back into play. So we have intramolecular forces and intermolecular forces. An intermolecular force is an attractive force between molecules. An intramolecular force is a force that holds atoms together. You know, intramolecular forces. Our intra forces are covalent bonds and ionic bonds. That is what holds a molecule together. So, for example, carbon dioxide. These double bonds are covalent intramolecular bonds. Intermolecular bonds occur between molecules. So that would be like if I have two separate CO2 molecules. There are attractive forces between these two. And the attractive forces between these molecules are known as the intermolecular forces. So inter, in between molecules. Intra, inside the molecule. Now, there is a difference in the strength of, the strength of inter and intramolecular forces. So here's an example. It takes 41 kilojoules of energy to vaporize 1 mole of water. What is vaporize? Vaporization. So to change water from a liquid to a gas, for every 1 mole, you have to apply that many kilojoules of energy. So what's happening when water goes from a liquid to a gas? Well, a liquid, they're close together. Here's my liquid. And there are attractive forces between them, intermolecular forces. And so to make it a gas, these molecules have to become really far apart. So you have to break apart these intermolecular forces. So then they can become a gas and spread out. And to do that requires 41 kilojoules of energy for every mole. But if you wanted to break the OH bonds in a mole of water, so I wanted to break this polar covalent bond, it would require 930 kilojoules to break apart all the OH bonds in 1 mole of water. So generally, intramolecular forces, the forces between molecules, are much, much weaker than intramolecular forces, the forces that hold together a molecule. And so there are a few ways you can kind of tell how, quote, strong an intermolecular force is by looking at its boiling point. So at what temperature does it go from a liquid to a gas? Generally, the higher the boiling point, that's telling us that there are stronger intermolecular forces because it requires more energy, a higher temperature, to make it a gas. Same with melting point, which is the temperature at which it goes from a solid to a liquid. And then these delta H's, these are the enthalpies of vaporization, fusion, sublimation. You learned this in 10th grade chemistry. You might not remember it, but whenever I look at, let's say, a heating curve of water, so this bad boy, water at 0 degrees Celsius is a solid. From 0 to 100, it is a liquid. And then from 100 up, it is a gas. So enthalpy of vaporization was this flat line. This is where the phase change actually occurs. It occurs at the boiling point, but once you get liquid water to 100 degrees Celsius, it's not automatically a gas. You have to put in a lot of energy to break it apart, as I just said, because you're not breaking apart the water molecule. You're breaking apart the intermolecular forces, or the attractive forces between these molecules. And that's the delta H, or the enthalpy of vaporization. So how much energy is required to break that? And so all of these tell us how strong intermolecular forces are. The higher the value, the stronger the force is. And so, to determine what intermolecular forces exist between molecules, we first have to do two things. One, you're going to have to draw the Lewis structure of the molecule, and then you're going to have to determine if it's a nonpolar, polar, or ionic compound. That will always have to be step one. And so we have 6 types of intermolecular forces. This video will go over 3 of them. The first type is known as London dispersion forces. You might have heard of this as van der Waals forces. Same thing. And you'll see London dispersion forces abbreviated as LDF, because who wants to write that word out? So London dispersion forces are forces that exist between any 2 molecules. Polar, not polar, doesn't matter. And so what it is, it's an accidental, instantaneous dipole that occurs in an atom, and it can induce a similar dipole in a neighboring atom. So I hope you recognize that word dipole from polarity. A dipole is a difference in charges. And so let's pretend I have 2 chlorine atoms. So I have 2 Cl2s. So Cl2 is an atom of chlorine and another atom of chlorine, and they're connected by a single bond. So they're sharing 2 electrons. But inside those chlorine atoms, they have protons and electrons. We're not talking about the electrons being shared, the electrons in those atoms. And randomly, because atoms have a positive nucleus, the electrons that are around them are negatively charged. The electrons might move to one side. So here, let me draw a better picture. So here's my nucleus. The electrons just might all randomly, and it happens, they go to one side. And when they do that, we have an instantaneous dipole, because for an instant, there's a difference in charges. This right side of the atom has a negative charge. The left side of the atom doesn't have any electrons, so it has a positive charge. And this just happens instantaneous. But when this atom is by, and I don't like ignore that picture, another atom that is neutral, that can cause a instantaneous dipole as well. So there's my positive, and if this atom gets near that atom, well, this is a negative. What do we know about electrons? Electrons repel electrons, and so the electrons move over on this side. And now we've got a positive and a negative. And this just happens randomly, and it is very short-lived. But for a moment, there are dipoles in these atoms, and because they have charges, there's an attraction between them, because negative attracts positive. Now, it is a weak force, or a weak attraction between them, but it is there, and this happens all the time. Electrons are always moving, and so sometimes they end up on one side of the atom compared to the other. And that's all London dispersion forces are. And this happens in any atom, any molecule. Here is a few good pictures. So right here just shows randomly 2 helium atoms. Look, the electrons are over here, so that side's negative. This side is positive. And these electrons, they come over here because they got close to that helium atom. They're attracted to that nucleus, and it just randomly happens. And so there's going to be an attraction there. And here's another picture with our partial positives and our partial negatives labeled. And again, they get close to each other, electrons randomly move. So the electrons would be on the left side of this element, while there's the partial negative, leaving this side partially positive. And then what do you know? This atom gets close to it. Now it has random dipoles, and there's an attraction between them. And then some other pictures for you to look at. So this up here, this is a big hydrocarbon. This is a non-polar molecule, so normally you wouldn't think there would be any attractive forces between them, but there are. There are London dispersion forces between them because randomly electrons will move around. And as this picture shows, they randomly went to this side of the molecule, causing a temporary, it's temporary and short-lived, negative dipole, which makes this molecule near it. The electrons will rearrange, giving this side a temporary positive dipole, and then they're attracted to each other. And then down here is a picture of a bunch of Cl2 molecules. So in between the Cl2, we've got a nonpolar covalent bond, which is an intramolecular force, or an intramolecular bond. And then in between the Cl2 molecules, we have London dispersion forces, attracting them together. Now, not all London dispersion forces, or the attractions between molecules, are super weak. There are some things that make it stronger. So this word, polarizability. Okay, I'm not going to lie, can't pronounce that. Doesn't really matter. So this indicates the ease at which the electron cloud of an atom can form a temporary or induced dipole. So the greater the polarizability, again, not trying to win a pronunciation bee, if that was a thing, then the greater the London dispersion forces. So a few things that make London dispersion forces stronger. As atomic number goes up, electrons go up. If there are more electrons, then the probability of getting a random dipole increases. And so larger molecules that have more electrons have stronger London dispersion forces between them. So if I have two F2 molecules, F2, F2, they're going to have London dispersion forces between them. And if I have two I2 molecules, they have London dispersion forces between them. Which one's going to be stronger? The I2 would be the stronger LDF, because iodine is a bigger atom with more electrons. Also, the shape of molecules can affect the strength of London dispersion forces. So, long and thin molecules are more, I'm not even going to try to say it, and they've got stronger London dispersion forces between them. Long and thin, so think like, and I'll show you an example right here, like butane. You see, it is long, it's thin, there's a great amount of surface area, or a greater, than something that's not as long and thin. And so if there's greater surface area, then there are stronger LDFs, because there's more space for electrons to move around and induce dipoles. So this picture I wanted to show you has butane and isobutane. Butane is long, it's thin, it's spread out. Isobutane is kind of chunky, and it might be hard because y'all aren't super familiar with organic molecules to tell the difference between them, But in isobutane, they have the same formula, but you can see it's kind of chunky versus over here they're longer and thinner. And so butane has the stronger London dispersion forces. Now remember, this would exist between two butane molecules. So a butane and a butane have stronger London dispersion forces than an isobutane and another isobutane. These forces don't exist inside the butane and the isobutane. They are between molecules of it. And so butane has a stronger London dispersion force. So what does that mean? The boiling point of butane is going to be greater than the boiling point of isobutane because it's got stronger dispersion forces because it's a longer and a thinner molecule. Something else that affects the strength of LDFs are pi bonds. And if you don't remember pi bonds are inside double and triple bonds. And so if there are pi bonds, the London dispersion forces will be stronger. Quick review, a double bond is 1 sigma, 1 pi bond. A triple bond, 1 sigma, and then 2 pi bonds. So double or triple bonds makes the London dispersion forces between molecules stronger. So, London dispersion forces are first type of intermolecular force that happens between any two molecules. We're going to talk about dipole-dipole forces next. So these are forces that occur between polar molecules. So you have to first indicate is your molecule polar or not. And what happens is polar molecules, like HCl down here, as you know, they have dipoles. And these dipoles attract them to other polar molecules. So in this picture, we've got the positive end of the hydrogen is attracted to the negative end of the chlorine. And the polar molecules will orient themselves to where this occurs. The positive ends are near the negative ends. And again, here's another picture. So they arrange to where positives are near negatives because positives and negatives attract each other. And this occurs between polar molecules that have dipoles always. London dispersion was between any molecules because even neutral things that are nonpolar can get dipoles when the electrons move around. So some characteristics of dipole-dipole forces. They are approximately 1% as strong as covalent or ionic bonds. So it is much easier to break this bond, the dipole-dipole force, than it is to break the bond between atoms. Dipole-dipole forces, their strength will decrease as the distance between dipoles decrease. So let's say I have HI and HF. And I've got HI, which has positive, negative, HF, positive, negative, and they're not near each other, but they're near another HF and another HI. HF, I hope you know, fluorine is smaller than iodine, so this would be the stronger dipole-dipole force because the distance between the dipoles would be smaller. They're smaller atoms. And then the closer they can get to each other, the stronger the forces. Also, the strength of dipole-dipole forces increases when substances are more polar. So I have a picture here of Cl3H, and it doesn't matter. There it is. And there are this is a polar molecule. There are dipole-dipole forces between the two molecules. We have our dipoles written. Now, if I had, let's say I had I had this molecule. So, CH3I. And I wanted to know which would have the stronger, what would be between them? which would have the stronger dipole-dipole force? The one with the 3 chlorines or the one with the iodine? So I hope that you know that carbon and chlorine is a more polar bond than carbon and iodine would be. How do we know that? Electronegativity differences. There's going to be a bigger difference between these two than these two. So this would be the stronger dipole-dipole force than this. This one would be the weaker. And then hydrogen bonding. So don't let the name fool you. Hydrogen bonding is an intermolecular force. And it is a significantly strong type of dipole-dipole forces. So these occur in molecules that have a hydrogen atom bonded to a very electronegative atom. Specifically, you need to have hydrogen bonded to nitrogen, oxygen, or fluorine. And so you need to have one molecule that has one of those bonds, H connected to N, O, or F, and then it needs to be near another element that has an O, N, or F. So for example, I have water. Water has oxygen connected to hydrogen and another water molecule. And let me draw a third one. So there would be hydrogen bonds, and I'm going to use my highlighter between, and let's circle my molecules so you don't get them confused. There would be hydrogen bonds between this oxygen and this hydrogen. There would be a hydrogen bond, which is just a really strong intermolecular force between this oxygen and this hydrogen, and this one, and this one. And this would keep these water molecules together. It affects their melting point, their boiling point, their enthalpy of vaporization, enthalpy of fusion, etc. Here are some other pictures of examples. So water connected to water is a hydrogen bond. NH3 by another NH3 is a hydrogen bond. Right here we've got NH3 by water. That would be a hydrogen bond. You can have NH3 near HF. That would be an H bond. So you have to have in your molecule H connected to O, N, or F, and it needs to be by something else that has O, N, or F. So for example, where there would not be a hydrogen bond. If I have water, and I'll even make this molecule polar. CH3Cl. There would not be hydrogen bonding between these molecules. The OH has the water has the ability to form a hydrogen bond, but none of the atoms in this molecule are electronegative enough. They're not N, O, or F to form a hydrogen bond. So there would be no hydrogen bonding between these two molecules. It has to be, you've got an H connected to an O, N, or F, and then it's by another O, N, or F to form a hydrogen bond between it. And so why does hydrogen bonding happen? Because bonds are really polar. The difference between hydrogen, oxygen, nitrogen, fluorine, that is a very polar bond. And then also, it's not just the polarity of the bond, the size of hydrogen. Hydrogen's a really small atom, and so those dipoles get near each other. And hydrogen bonding affects so many things and so many physical properties of molecules. We wouldn't be alive on Earth, we wouldn't be able to live on Earth, and we wouldn't be alive probably life wouldn't exist if water wasn't able to have hydrogen bonding with other water molecules. So hydrogen bonding is extremely important. So today I went over the 3 types of IMFs. 3 types. There are more types. There are more videos to watch. London dispersion forces, dipole-dipole, and hydrogen bonding. London dispersion forces are the weakest to hydrogen bonding, which would be the strongest. And London dispersion forces happen between any molecules. Even water molecules have London dispersion forces between them. Dipole-dipole only occurs between polar. Hydrogen bonding only occurs between if you have an H connected to an O, N, or F, and then it's by an atom with O, N, or F. And then something else I didn't throw in that I need to about hydrogen bonding before I forget. If we have a solo HF, HO, and HN, the HF is going to form a stronger hydrogen bond than something that has a solo OH or a solo NH. This would be the strongest because that's the biggest electronegativity difference. Now this messes people up because if you look at HF versus HF and then water has, sorry you can see that, water has a higher boiling point. So water has a higher boiling point. Water, I hope you know, boils at 100 degrees Celsius. HF boils at, hydrofluoric acid, boils at 67 degrees, Fahrenheit, that doesn't help, 19 degrees Celsius. And so what's the difference? I just told you HF is stronger. Why does water have such a greater boiling point? Because water has the ability to make multiple, it's got 2 H's on there, it makes multiple hydrogen bonds on both sides. Versus HF, which is just a HF, positive, negative, HF, positive, negative. It can't make as many hydrogen bonds between molecules as water can because it only has that one bond. So when you're comparing the strength of HF, OH, and H bonds, yes, HF will have the stronger hydrogen bond, but you have to also compare the number of bonds there are. So how many things have H attached to an O, N, or F? Because the number will influence as well.